Now that we've looked at the fundamental theorem of calculus part 1, let's do the part 2. If f is continuous on the closed interval a to b, and big F is any antiderivative of little f on a to b, then the integral, definite integral from a to b of little f of x dx is equal to big F of b minus the big F of a. So essentially, by evaluating the antiderivative at b and at a and subtracting those, we find the definite integral. This is how we're going to calculate it. So let's calculate a few problems here. Let's start with the integral, we'll say from 1 to 3 of 3x cubed minus 2x plus 1 dx. So the first thing I'm going to do is I'm going to find the antiderivative. Now it does say any antiderivative, and we'll talk about that, why that is, but I'm going to choose the most general antiderivative for starters. And so the antiderivative of x to the third is x to the fourth, but because there's that 3 and 4th in front, it's going to have to be a 3/4 x to the fourth, minus, this will just be an x squared, the antiderivative of x is x squared, and the 2 works out, plus x, and then like I said, I'm going to use the plus c. Now, I do need to evaluate this from 1 to 3, and so how I indicate that is I put in parentheses and I put a bracket at the back with a 1 and a 3. The other thing you will see too is a lot of times you'll see just a straight line, and you can do that too. So you might just see that. It's just that a lot of times my straight lines look like ones or absolute values, so I turn them into brackets a lot of time just so I can see what I'm doing. But some indication there that we still have to evaluate from 3 to 1. So let's start with the 3 first. I'm going to plug the 3 in. So I'll have 3/4, 3 to the fourth, minus 3 squared, plus 3 plus c. That is all for the 3. I must subtract from that 3/4, 1 to the fourth, minus 1 squared, plus 1, plus c. Now, I'm going to start subtracting these things, and I've got some larger numbers to work with too. But notice the c's are in both cases, and they're not just numbers. They're not going to just blend in with the rest of it. But what I do know is if I have c minus c, those things are going to cancel. And that's why we don't care about the most general antiderivative. It never says the most general. It just says an antiderivative, or any antiderivative really, in fact. We don't need to write those c's when we're looking at a definite integral. We have an indefinite integral, which remember we can tell because there won't be any bounds here. We've got to have that plus c there every single time. We have a definite integral, we don't need to write it down because it's just going to cancel out. So let's finish out this problem. So we have 3 to the fourth, which is 81 times 3 will be 243 over 4. Then we have 3 squared, which is 9, plus 3, minus, we'll have 3/4, then we'll have minus 1 plus 1. And so I'm going to work with the fractions first. We'll have 243 minus 3 over 4, and 240 over 4 does simplify to just 60. So we'll have 60 minus 6, and then the ones back here would cancel out. So I did the 243 minus 3/4, gave me 240 over 4, which is just 60, and then this is just a minus 6. And then fully simplifying this, 60 minus 6, we get a 54. And that's my answer. Let's do a couple other examples, but they're all going to be equally as easy. Once we understand what we're doing, it's just the same. So let's take the integral from -1 to 0 of 1 over x plus 2 minus sine x plus 1 dx. So if I look at this first term, the antiderivative of 1 over x plus 2, well, remember, anytime we have the 1 over x, it is the natural log, right? Because if I have 1 over x, I can't just increase that exponent by 1 because then we'd have x to the 0. The whole way we get the 1 over x is by starting with a natural log, and we'll have x plus 2. Notice I do add those absolute values around the inside the natural log. Not necessarily necessary if we have something that's going to work out to be positive, but we do we can only take positive natural logs, so this is always going to have to be an absolute value there. The antiderivative of sine is cosine, but if we think about taking the derivative of cosine, that would give us a negative sign, so here I'm actually going to put a plus, not a minus. The derivative of cosine is negative sign, so that works out. And then the antiderivative of 1 is x. And I'm not going to bother putting the plus c because it's definite integral. I need to evaluate this from -1 to 0. So I'm going to start by plugging in the 0. Natural log of 0 plus 2 plus cosine of 0 plus 0 minus the natural log of -1 plus 2. And notice I've dropped the absolute values. I recognize them both of them. They're positive, so I don't need them once I recognize I have a positive in there. Plus cosine of -1 plus 0. And so when I simplify all of this, we'll have the natural log of 2. Cosine of 0 is 1. And 0, I don't need to write that down. And then we'll have minus the natural log of 1, which is just 0, minus cosine of the -1. And cosine of -1 doesn't give me an exact value, so I'm just going to leave it as the cosine. But just to finish simplifying, we'll have the natural log of 2 plus 1. Natural log of 1, remember, is just 0, minus cosine of -1. And there's my answer. That's all there is to it. So as long as we can find those antiderivatives, and as long as we remember the order in which we subtract, we always take the upper minus the lower. As long as we remember that order, it's a relatively simple process to find these definite integrals.